Okay, let's start. So very warm welcome, everyone. So yeah, we are rolling again after a long time. First on-site again event. Actually, we are trying to do it hybridly. So there's also people online. Yeah, and we have a super interesting event today. Thanks everybody for coming. But before jumping into this, I would like to share a few other exciting news. The first one is we also have now a new course on applied reinforcement learning, and as far as I know, it's the first one such course for professionals in Switzerland. So yeah, if you're interested in this, it's really focused on building IELTS solutions for real-world problems. So then you can, if you wonder how to find it the best way, I put the link here on our meetup page under discussions. You can find the link there. And there's also some other similar courses maybe you're interested in, like deep learning, digital ethics, or ML ops, and others. So you can have a look. And yeah, so that's about learning about IL, how it works, but then often the main challenge is actually to find a good use case. And that's why for the next event, we are planning to do something different, and that's to have a workshop. That's together with the Data Innovation Alliance. And so it's meant like a brainstorming, so everybody can think about possible IL use cases in your organization. And for this, we are still looking for a speaker who can present one use case so that we can get inspired and in our brainstorming. It doesn't have to be a complete project. A concept level is fine already. So in this case, please let us know. That's the email address. You find it also on the meetup page. And then finally, the next step, if you already have a concrete idea, maybe we can work together. I run a little research group focused on reinforcement learning for industrial applications. And yeah, so that might be funded with InnoSwiss. Okay, so coming back to today. So let's get inspired what other people are doing. And we have some very exciting topics. And of course, finance is all about time series, and RL is about optimizing decisions on time series. So it obviously kind of makes sense to put the two together. And yeah, so let's get started. Yeah, so our first speaker for today is Dr. Alexander Bost. He has a PhD in theoretical physics, and he works as a senior lecturer at the Institute of Wealth and Asset Management at ZHAW, where his research focuses on green tech and AI for finance. He has more than 12 years of experience in the financial industry and several positions, and the last one as the head of research and portfolio management at the Swiss hedge fund. So, Alex, we're looking forward to your presentation.
Thank you very much, Klaus. So I'm very happy that you mentioned that you're looking for use cases, actually trying to bridge the gap of the theory of reinforcement learning and its actual applications, right? Because as I will outline in my little introduction, this is exactly why we started the project we are about to present here today. And we are actually very happy and would like to say thank you to meet up Reinforcement Learning Zurich and Klaus for inviting us today so that we are able to present our project and our findings, our first findings here. And of course, we are also very happy and would like to thank ZKW here for providing this very nice room and the very nice infrastructure for our talk. I will just give you a little bit of introduction, right? Introduce the project and the idea we had when we started this, and then Fernando and Florin will take over and talk about all the interesting stuff. So let's have a look how it all started, right? And this was actually with an innovation check we had some years ago with Private Alpha. They approached us and they thought about what can we do, how can we can come up with some way of devising a nifty trading strategy. And we started this innovation check here through deep learning, neural networks. As a proof of concept, what can be done and how we can actually look into self-play, how can we look into reinforcement learning in order to apply this to problems in trading, devising new trading strategies here. And we came up with this proof of concept, and it was really successful. So they liked the result. We wrote a little report. We even managed to get this report placed as a paper in a journal. And then, of course, we thought, yeah, what else can be done, right? So now that we have the proof of concept, we of course wanted to advance this, and basically we thought about an innovation project. To tell you the truth, that was not really how it started. It really started all with me playing StarCraft for I don't know how many years, right? And then finally, after all my decades-long experience, I learned that they train AlphaStar to do exactly the same thing, to play StarCraft 2, right? And when I read the blog and when I read the videos beginning of 2019, when I read and looked at the recorded matches, I was actually looking like these guys here, right? Because it was awesome. It was like AlphaStar not only managed to play very successfully and beat the best players, best human players internationally, the AI actually came up with new and exciting strategies which no human had ever devised before, right? And they were successful. So it was really mind-boggling for me. And here you can see the MMR. And just for reference, I was always kind of competing at platinum, sometimes diamond level, and I thought myself, that's quite good, right? Before I learned that the best human players actually had an MMR double of mine, and this was even exceeded by the AI. And we met at Private Alpha, Marco Fresh, and he was also into this, right? And he had also the same mind frame and said that basically if I can learn something as complex in a real-time gaming simulation, why shouldn't it be able to learn also how to devise an optimal trading strategy? So we filed an Illustris innovation project for this together with Private Alpha, and this unfortunately didn't work out, right? It got rejected because of the very simple reason that basically Illustris told us, yeah, you want to devise a proprietary trading strategy for this business partner here, and we're not funding this. It does not scale across the industry, and you need to do something better. So basically, we went back to the drawing board after we got rejected, and we thought about, yeah, but what would be the actual benefit for the Swiss financial industry? And we talked to a lot of more stakeholders, and basically the answer was exactly what Klaus already mentioned, right? Everyone was kind of very, very convinced that there is something in reinforcement learning which can be used for finance. But everyone also told us it's a high project risk, we don't have the resources, we think there is something, but we can't commit to actually trying to unearth the potential there. And that's basically where we thought, okay, let's take a step back and let's do this with Illustris funding, but no implementation partner. Let's kind of devise a strategy. Let's go through all the pains and try to identify the roadblocks when you want to apply reinforcement learning in finance. And we want to do this with use cases, right? So not only with theory, but actually coming up with use cases which we identified with our stakeholders in the financial industry. And then we set to work actually solving and implementing these use cases from scratch. And for that, InnoSwiss was happy to provide us with a little bit of project funding here. So we started this project. It started roughly a year ago, and we still have like half a year to complete the last use case we have in our pipeline. And we still have some time left to somewhat wrap it all up and come up with nice findings here. Basically, here you can see an overview of our project here, which we are currently running. Here's the team. Division I already basically ran you through. With the use cases, what you will see today is optimal execution with reinforcement learning. Then we looked at the second use case, recommender systems. That was quite promising, but we couldn't get the data. Right? We needed data which the banks are very reluctant to hand over to us for obvious reasons. And then today we will have an outlook for factor rotation. And the actual last use case, which you can see here, multi-agent traded systems, that was kind of our dream. The dream we had in the beginning when we looked into this proof of concept together with Private Alpha, but it turned out that we needed to kind of advance in very slow ways here. So the question is whether in the project we will have still time for looking into this, but it is for sure something which we will explore in the future. For our project here, we have our own GitHub page, right? We also have a LinkedIn page, and you can find all the details there, either in the ZHW database or in the InnoSwiss database, if you're interested. Yes, and with that, I would like to conclude. On the last slide, I have a lot of text, right? Which basically I hope I didn't forget anything to mention, but here it's all wrapped up in a nice way. Yeah, and then without further ado, I would like to hand over to the actual experts here who will run you through the first use case. Thank you very much.
So this part of the project was led by Christoph Out, who unfortunately cannot be with us today. But and he is also a senior scientist at ZHW. But our two speakers that we heard from now is, I think the first one, Florin Dascalu. Yep. He is a research assistant, and his interests are in systematic strategies, synthetic data generation, and machine learning. And then also will be shared with Fernando de Meer Pardo. He's a PhD student in the same team, and he specializes in deep generative models.
Okay, hello. Today we are going to talk about optimal execution in using reinforcement learning. First of all, let's have a small overview. Where is reinforcement learning in the big scheme of things? And we see that in this page. So we have the supervised learning and something like this, and also on the right, the reinforcement learning. Now, what is the big difference between what we have on the left and what we have on the right on the reinforcement learning? So basically, the biggest difference would be that in reinforcement learning, the agent is having an impact on the data. And also on reinforcement learning, the data is generated while learning. So basically, some sampling is done in an environment. While on the left, we already have all the data, and basically we are feeding once all of them, and thus also a very powerful thing that reinforcement learning can do is to work with when there is a temporal delay between an action and the effect, and this is quite maybe not possible to be modeled in a supervised learning. So let's see a little example here. As I said, reinforcement learning is very well suited for sequential decision making. And in this schematic on the left, we have clearly two modules. So we have the agent and the environment. And the way that it works, so first thing, the environment is going to be reset. So basically, it's going to return a snapshot of the game. So you see we have a little card there. So all the pixels are maybe done some transformation, and then the agent is receiving this. I mean, it can see this observation at T0, let's say, and then based on this, the agent is going to take an action, and then again the action of the agent is fed back into the environment, and then it's going to run for a number of steps. And at each step, the reward, I mean, the environment can return not only the observation, but also a reward. And this is one of the targets of reinforcement learning is trying to do some sampling on the environment, and it tries to increase the amount of reward during training. Okay. Also, sometimes depending on the environment, the reward can be either sparse or dense, and usually it's much better to have a dense reward. So after each loop, after each step, a reward is returned, so the agent can better, so the agent can know better if the action was good or not. And there is an issue if you have very sparse rewards, so the agent is applying different actions, but it's going to find very late if it was a good action or not. And for these, there are some strategies to be used in the exploration, like intrinsic reward and some other random autoencoders and stuff like this. And here's a practical toy example. So we have an inverted pendulum on a cart. This can easily controlled by classic control, but we can also use in reinforcement learning. So what we have here, so the X would be the observation is composed of the place of the cart, so on the X-axis, and also we have the theta, the angle of the pendulum. The action here would be to try to apply a force to the left or to the right of the cart, and here the reward would be to keep the pendulum upright. And this is quite a nice example because for sure we have that feedback effect. So when the agent is going to provide an action, it will move the cart and have that feedback effect. Of course, you can have some more examples, but the thing is that there is a difference between games and finance when it comes to reinforcement learning. So the thing in games is that usually the environment it's either deterministic or it has some Markovian properties. So it can learn, and if there are no bugs in the engine of the game, then it's going to learn it pretty well. And we have an example. As you can see, the hide and seek by the OpenAI, and the things that at the beginning they were random actions, and after a few million iteration episodes, basically the hiders learn how to hide from the seeker. But as you can also see that one of them, they're grabbing that ramp, because actually in the meantime the seekers were learning how to use that ramp to go over the wall. So it seems that it can be applied to some more complex games. And as I said, in games it's pretty, let's say, easy. But in finance it's more complicated, because in finance, so in time series, we have a lot of interesting things. So, for example, some stylistic facts, volatility, some jumps about the correlation. The biggest issue will be non-stationarity. And this is quite a bad thing, because the reinforcement, the agent is going to learn, so it's going to sample the environment. But as we know in finance, for example, the correlation, they work till they don't. When there is a big structural change, the correlations are very different. So basically in the finance game, the rules change in stochastic way, and this is an issue. And as Alex mentioned, yeah, we can, I mean, we should appreciate how powerful and how complex reinforcement learning on StarCraft can be, because just imagine the number of steps that is needed for the, of course, they started in the Alpha Star, they started with the supervised learning first, so they took a bunch of training from the already some recorded games, and then some transfer learning, and then switched to reinforcement learning. And yeah, they did the human intent one, the best one. Regarding our implementation, so we are happy that we have this nice DGX machine at our university. It's quite a powerful one, 40 cores, 4 GPUs, Tesla, quite powerful, water cooling, and so on. And for the stack of the software, we used the GIM for the environment as very common, while for the reinforcement, for the reinforcement learning part for the RLib, we also use a stable baseline, but it is not so mature, and there was some issue also. For example, some recurrent network, we couldn't find the latest version. So we tried with Ray, RLib. The issue is that Ray is a very powerful library, and it has quite a steep learning. Although, yeah, once you get the feeling of it, it's easier. But it was quite complex. And also, there's a big issue if you want to do some debugging on the RLib, because of the abstractization. It's quite complicated. And regarding the algorithm that we're using for our project, it's a special version of the PPO, so the asynchronous one. And this is nice because, so it's based on the Impala. There is a nice paper about it. The thing is that in reinforcement learning, it's quite inefficient to do the sampling. So as in supervised learning, you already have the data, but in reinforcement learning, you need to do some sampling in the environment. And usually, or sometimes you can use a synchronous one. So the agent is providing the actions for the environment, and then the environment returns the reward and the observation. But this can be done asynchronous too. So APPO, so asynchronous PPO, this is very good at it. So basically, you can launch 40 environments in parallel and try to do sampling continuously. And from time to time, also send back the observations to the learner. Of course, there are some trade-offs. The issue that if the worker, the robot worker, is too old and the trainer is too new. There is a mismatch of weights, and this can be an issue, but can be tuned. Regarding the data that we used, so we started with some crypto data because it is quite hard to get any level 2 data for other time series. So we are recording for quite some time. We are subscribed to WebSocket, and Binance is providing. So the type of the contract, the Bitcoin dollar here. So it's not. It doesn't represent the transaction on the blockchain, but it is on like a future exchange. So it's a matching engine. So there are quite some some activity over there, and they're providing roughly at 100 milliseconds interval snapshots of the LOB. Yeah, best 20 ask and bids and the quantity, and we upsampled from 100 milliseconds to 1 second. Yeah, so we have roughly about 2 years of data, but we are still a little bit far from using all of it. So, yeah, that's what I said.
So now we're going to jump into the actual root of the problem that we want to do. So basically, what is an optimal execution, and why is it a good idea to use some kind of reinforcement learning with it? Basically, the problem of optimal execution is the problem that any kind of participant in the market faces, right? When she or he wants to buy a set amount of shares of a given asset, and it has to do it on the market somehow. In the market, we're used to seeing the numbers and seeing how the numbers on the graphs go up and down. But the reality in the market is that you have to interact in the market in some kind of way. You have to submit what are called orders. And an algorithm to basically perform optimal execution has many options to choose from. Basically, when you want to take a really big order, normally what you do is you divide it a lot across time, and you divide the volume. You do this with child orders, and you have to choose basically how much volume, so how much quantity of the big order each child order is going to have. You need to choose how many child orders you're going to submit as well. You have to choose when across the execution horizon you submit them. And also you have to choose which type of orders you want to submit. Because in the financial markets in general, these are the two main types of orders. There are a lot more, and they can get quite complex. But basically, market orders and limit orders are the main ways that people have, participants have of interacting with the market. It is a nice idea to use reinforcement learning to carry out optimal execution, because it's basically the type of problem you would want to use RL on, because it's a sequential decision-making process whose outcome is decided in a stochastic way, right? So depending on the states that the environment presents the agent with. And of course, every decision made along the execution, made along the episode, in this case, or on the reinforcement learning problem, affects later decisions down the line. Classically, the way optimal execution is done, and if you have, if you go buy an algorithm for an algorithm vendor to interact in some kind of market, there are algorithms that have actually really simple rules. So the by far most commonly used one is simply the time-weighted average. So what you do in a time-weighted average is very simple. You have to execute an amount of given volume, and what you do is you distribute the orders evenly across time. So here you only have to choose like what amount of orders do I choose, right? The volume is automatically given to you. Another way to do it is with a volume-weighted average price. So in this case, instead of trying to capture the time-weighted average over the execution horizon, you try to somehow incorporate the volume that you've been observing in the market along with it. So you place your orders according to some volume-weighted current price. These algorithms are built on very simple logic, right? There's not really any magic going on behind it. They're really simple rules. So the question that we had when trying to develop this project was that, okay, so these algorithms don't look at the LOB at any moment, right? Can we have a reinforcement learning setup that basically manages to outperform these two very simple setups by looking at the information present in the LOB, right? Can this be achieved? It only makes sense to, have reinforcement learning, to use reinforcement learning in this case, if we manage to consistently beat these kinds of algorithms, right? Because basically reinforcement learning is this hugely complex algorithm. At the end of the day, it's a huge neural network. It's just a really black boxy kind of algorithm. Whereas these two algorithms are very, very simple, right? You always know why the decisions are made. And when dealing with such a delicate thing as executing orders in the market, interpretability is an important thing. So it only makes sense to use this kind of setup if we manage to consistently beat these kinds of algorithms. And this is going to affect a lot of decisions in the setup, as you will see. So to convert the data that Florin was talking about into the RL setup, we have to first see a bit more in depth what kind of high frequency data we can come across. So colloquially, high frequency data is divided into these three categories that are referred to as levels. Level one data is basically only the price data of the given market, including maybe or maybe not the best bid and ask prices, and maybe their volume. So this is the most smaller kind of data you can have, but it gives you very little information because it doesn't give you information on price levels beyond the best bid or best ask. So you only have an information of like where were the latest prices traded at and where is it most likely to trade next, because you only know these first levels. When you add more levels to the LOB, you get what is commonly referred to as level 2 data. So adding the n best bids and asks of prices and volumes, so you have a much bigger LOB and you have more information on what's called the depth of the market. So you can see that it's not only the participant at the best prices that is trading, but there's also a lot more people waiting to trade at other price levels. And then the best kind of, the most complete kind of data, high frequency data that you can have is level 3 data. So in level 3 data, you don't have what you have on the other two previous levels, which are only like snapshots of the LOB. In level 3 data, you only have order placements, right? So that you can know where the volume of each price level comes from. And the problem is that, of course, as the data becomes more detailed, it gets more expensive and sometimes even inaccessible. So level 2 data is usually really easy to access and it's probably free. Level 2 data can be harvested with APIs of Binance in this case, which is what we're doing. But level 3 data is much more difficult to come across. So it's either paywalled and behind really high paywalls. So for example, there's a service called Lobster, and in Lobster it's called like, it's a joke on LOBs basically, the name. Lobster costs around $5,000 per month, and it only gives you access to one LOB of a given market. And it doesn't even give you the whole LOB because it only gives you like across certain times that they sample from. So level 3 data is really inaccessible. And that's why in this project we're using level 2 data because, for example, Lobster only gives you data on the NYSE, on the New York Exchange. But in many cryptocurrency exchanges, for example, there's not even any record of level 3 data because either they don't want to give it out because they don't want to sell it, or even because they don't record it, right? Because level 3 data can amount to huge data sets because it's all the orders placed at a given exchange. So yeah, level 3 data is basically, it is the best standard that you could work with, and it would be ideal in this case for reasons you're going to see later. But the world is not perfect, so we have to settle with level 2 data. When you have an order book, you basically have this huge array, right? In which you know all the volumes at given price levels. And you have, yeah, as I said, this LOB data that we have. You have to build observations from in order to have a RL setup. Many papers, what they do is they take the LOB and they do some feature engineering. So they calculate some statistics from the LOBs that they have. For example, very popular statistics are the trade and volume imbalances, the running mid-price volatility, the drift, etc. However, the problem with choosing which kind of features you want to include in your observation is potentially bias inducing, right? And in this methodology, because we want to make it widely applicable, we want to kind of try to avoid this. So what we do is, instead of that, we simply fit the LOB that we have as the observation. We want to have an agent, that when showed with these LOBs, right, will tell us, how do we place the orders. If we give the LOB, the agent, too many choices, so all the things that I talked earlier, like the type of order, the time of the order, the price, the volume of the order, the RL problem basically becomes too complex to have anything working. So the most common thing to do is to restrict the agent choices and make it only, for example, choose the volume, right, of the order. Already say like, okay, you're going to trade at these times, that you can decide however you want across the execution horizon. And you can make it say, choose only the volume through the agent of your setup. One way to choose is, okay, as I already told you the time, I'm also going to tell you the type of order. So for example, if you make it choose a market order, this would be by far the most common choice in all the papers that discuss optimal execution with reinforcement learning. If you place a market order, you only have to choose the volume because the price is already given. Yeah, you are willing to trade at any price. The problem, as you will know, with market orders is that when you submit a market order, what you do is you run through the LOB, you eat into the order book. So you're risking yourself to execute a lot of volume and disadvantageous price levels, which is very undesirable. Of course, this is the easiest kind of order to choose from an RL standpoint, because most papers, what they do is they execute the order that the agent chooses against the observation, right? This is a big problem because, of course, in a real life setup, between your observation and the submitting of your order, there's some kind of latency, right? So the LOB that the order your agent submits faces will be completely different from its observation. But this is what most reinforcement learning papers and optimal execution choose to do. And this is why we made this the cornerstone of our project. So we said, okay, we don't want to do as everybody else does and submit market orders, because this also makes it so that the agent can int into the order book a lot and makes the eventual outcome, eventual algorithm very unstable for this reason. So we want to have an algorithm that is more robust. And the way to have more security when submitting orders is, instead of choosing to submit a limit order. So limit orders are nice because at the contrary from market orders, you have to specify a price that you're willing to trade at. And the disadvantage of limit orders is that you're guaranteed a price at which your order will trade in, but you're not guaranteed whether or not your order will execute. So this is, in reinforcement learning, it's also difficulty, because if you cannot use the same LOB that you use as observation to execute the orders of your agent, and then what you have to do is you have to run through the LOBs, right? Basically, when you place a limit order, you usually place it somewhere, not at the best bid, but somewhere very close. And you hope that future LOBs will execute your order, but not the one you're placing it at the moment. So what we do is we make it so that our agent can only place orders at the same time the TPOP algorithm places orders, and we only allow it to choose fractions of the volume. So we make it so it has a really simple action space, discrete action space with 3 dimensions, and it can either choose to submit 80%, the same volume as the TWAP, or 120% of the volume of the TWAP. Once we place a limit order, of course, we have to decide on how to execute it. This is also another of the big challenges. If we had access to level 3 data, the stream of orders, there would be no dilemma here, because we simply would place it at the current LOB that we use as observation, and we would match it against the incoming orders until it fully executes it. The problem is that we don't have level 3 data, right? We have level 2 data. So we have to basically decide on an algorithm to execute orders as realistically as possible to try and imitate a real market. So what we do is we place an order at the best bid or ask plus minus 1 tick. So this makes it so that you don't execute against the LOB that you use as execution, as observation, but you match your order against the next LOB, against the LOB in this case that we have at the next second. Of course, most of the time, because you're really close to the mid price, there's not going to be enough volume to execute your whole order, depending on the amount of volume that you want to execute. But most of the time, there's not enough volume. So if we see that our order was partially executed, what we do is we replace it again on the best bid or ask plus or minus 1 tick away, which is different from last LOBs. And then we repeat this process until we have the whole volume of our order executed, or until we end the reach of the execution time. So if we reach the end of the execution horizon, what we do is we place a market order so that all the volume is wiped out. So in this way, we kind of make the algorithm more robust because it's not placing market orders all of the time. So it's not going to eat into the order book so much. But we also have to do this process of iterating through LOBs, which adds a lot of overhead. So it is a trade-off because yes, of course, in one sense, it makes the simulation much more realistic, but on the other hand, it makes it much more slow because you have to do this iteration every time, and this is very hardware intensive basically. Of course, because we're recreating a real market from LOB snapshots, it is very important to keep in mind that this simulation, of course, at the end of the day, is a model, right? All models are wrong, but some models are useful. We have a lot of differences from our simulation from a real market. So because we only have level 2 data, we have only LOB snapshots. We really have no way of knowing whether 2 different volumes at 2 different LOBs come from the same order placement, right? Because it might just happen that from the data that we have, the same volume is just not executed between LOBs, right? But because the LOBs are the only thing that we can interact with, we don't know what is the order that it comes from. So we might be executing the same volume more than once. So in that sense, we might be overestimating the volume that there is available at a given time in the market. But on the other hand, because we only have snapshots of the LOB, we don't know the orders that were in between LOBs, right? Because they just come, they execute and they disappear. So we don't know any of those orders in between the snapshots. So in that sense, we might also be underestimating the volume, right? So this is the problem from having snapshots of the LOB only and not the full level 3 data. That you never know whether you're overestimating volume, underestimating volume, or you're getting it completely right. It is possible to know from this kind of data set, but it's something that you have to go through. We basically found out that when developing this kind of simulation, it is extremely important to, at the very beginning of the development, implement unit tests that you want your simulation to basically accomplish. Because all sorts of funny bugs can happen during the development, and some of them can be really unintuitive. The first one that we kind of saw was that using floats is a no-no, because here you have a given tick size, so you cannot get smaller than a tick size in a financial market. So for that, we have to use a different kind of data type, so Python decimals rather than floats, to avoid these rounding errors as well. The problem is that using these decimals, okay, makes it so that you follow all the logic of the financial market, so the environment, but outside the environment, the array logic that we use on top, so the Ray, the algorithms coming from Ray, can also have problems with this kind of data type. So we have to do a lot of conversions between decimals and floats, and we saw that if you do this too freely, this adds a lot of computing overhead. Another very unintuitive bug that we found is that unlike in a real market, when you only have LOB snapshots and you submit a market order to a snapshot, it may be that the volume of the order that you want to execute doesn't fully execute, right? Because the LOB simply doesn't have enough volume for you to match with. So not only you have to iterate through LOBs with limit orders, but you also have to do it with market orders. Of course, in a real market, you place a market order and it seemingly instantly executes, right? But when you only have snapshots of the LOB, you also have to take care of these things. Another thing that also happened to us during development was that, the way in which we have programmed the submission of the orders, the matching of the orders against LOBs, make it so that, of course, the LOBs mutate, right, between order placements. So you have to be really careful when using variables coming from LOBs, because, if you use it at different times of execution, they can lead to, very unintuitive, but at the end, problematic bugs. So now we get to the good stuff. Given that we already have an agent that can decide orders through actions, how to submit orders, how do we choose to reward this agent? So as we said earlier, it is really important to have an algorithm that outperforms the commonly used benchmarks for optimal execution. So it would be ideal as well if our reward function accounted for this implicitly. This, for example, can be done via Sparse Reward, which rewards the agent only at the end of an episode where the full outcome of the execution is known. And we can do this by comparing the performance of our algorithm to that of a benchmark algo. We can, for example, give a +1 or -1 reward, or we can simply do it with the dollar difference, right? So if you're selling, you would want to sell for a higher price than the benchmark algo, and if you're buying, you would want to buy it for a lower price than the benchmark algo. For example, if you use the dollar difference, it would somehow incorporate risk awareness into the reward, which would be nice, right? So bigger advantages. So making a lot more money than the benchmark is rewarded, and making a lot less money is punished. But because we're gonna compare two algorithms, this makes it so that at every episode, you have to fully simulate both algorithms every time. So of course, this adds complexity and overhead to the simulation. So apart from doing all of this, with all the training logic and of each component, you have to program, as you all are aware of, that you have to make an environment that we do with Jim that does all of these things, right? So it samples new execution parameters at the start of each episode so that you have a flexibility in choosing what kinds of the amounts of volumes that you execute, for how long you execute it, which benchmark algo do you compare it to, etc. It has to correctly present the agent with the correct sequence of LOBs. So it has to fetch well from the data, and it has to take into account timestamps. You have to make sure that you're never anticipating any data, of course, because then this whole thing is completely unrealistic. You have to process the agent's actions really well. So you have to convert this placement of orders, this choice of the volume, into the whole simulation of the algorithm. And you have to do it over multiple steps, right? So it's not like at every step you already know the reward, but you have to take the actions over the whole episode, and you have to take them all into account to, at the end, output the reward. And you have to calculate the rewards over the episode in an efficient way. The problem is that you have to make all of these things efficiently, because during training, as you're all aware, we're gonna need to train them millions of times, right? And it is, when you have so many moving parts, it is extremely easy to add computed bottlenecks without trying to do so. So this is another thing that needs to be kept in mind. So when we started training, the problem that Florin already mentioned is that, the very nice advancements in reinforcement learning have been done in game-like environments, right? Where you have a static transition distribution between states, and the agent tends to run into the same state often. In this kind of sense, it's really nice because you can even do hyperparameter optimization, right? So you can train a bunch of times to see which kind of set of parameters, hyperparameters, gives you the best performing agent. And also because you know that from training to evaluation, the environment is going to be essentially very similar because the rules of the game never change, right? But because we're dealing with real financial data, here the agent basically never faces the same state twice, so it has a much bigger problem with memorizing sequences of actions that lead to nice rewards. It's basically a dynamic transition distribution. We call it dynamic because it's simply when the states are generated from a real world data, they are just simply unknown, right? There's no way to characterize the distribution of states. If you could, you would be very rich, of course, but that's not the case. And the biggest problem here is that the states that the agent will be faced with are going to be very different from training to evaluation, of course, because they happen at different times during the market, right? So the most important thing is not to choose a set of hyperparameters that performs the best during training, but to actually choose a set of hyperparameters that is able to generalize, right? That is able to learn something from the training, and that's something that the agent learns can be applicable later down the line to different sequences of LOBs, right? Which will be the future, which will be the place where you would want to have a nice RL agent. One of the first challenges that we found was this thing that we plot here. So if we choose the dollar difference of execution as the reward, we simply have the problem that on a given day, we don't really know which is the maximum reward that can be achieved, right, with the type of actions that we made possible for our agent. This optimal reward is unknown and NP hard to compute because you basically have to, you have a polynomial computing time. So the way to tackle this particular problem that we had was basically to try and get some light into the process. And we said, okay, so if we have two different agents, two different neural networks that seemingly converge to the same maximum reward, then we can say that that maximum reward is the maximum reward that you will want to achieve on a day. And we would be happy with this kind of training. So we did this, this was one of the first experiments we did. And this, for example, training on one single day. And these are two different kind of agents. One of them is a really simple multi-layer perceptron, and the other one is a more complicated recurrent neural network. And here we saw, for example, that both of them reached eventually the same plateau. So we said, okay, so there is actually something that is possible to be learned, at least on one day. Another problem that we saw while training was that if we took the day, oops, I didn't never really put the microphone back. If we took the, yeah, this is too low. If you take the data set and you basically change between the different days across training. So we said, okay, let's change the data that we sample from every 500,000 roughly episodes. Of course, because the days are completely different between themselves, there are completely different sequences of LOBs because they're gathered from the real market. This makes it so that the agent learns something, but as soon as you change the date, you have this huge drop in performance, right? Of course, because it's a new, it's completely different data that it has never seen before. So we saw that if you do it this way, you sequentially change the days, which will be the first thing one would think of. You can run into a lot of trouble generalizing, right? And this is really bad for the agent because basically learns one day, but then you go to the next day. So it has to memorize the second day, but it forgets the previous day. And then it goes to the third day and it memorizes the third day, but it forgets all the ones before because they're all completely different. And we saw that, yeah, we have to kind of find a way of combining the data from different days in a way so that we can try to kind of avoid this during training. So we have to do, yeah, some magic on the sampling as well. We'll go through different days, but combine them all. Perhaps going through what we have been trying to do is do one episode on one day and then simply just jump to the next day. So this is what we've done here. We did this, I think, with this is 2 days only, and with the APPO algorithm that Florin mentioned earlier. Oh no, this is only 1 day as well. So this is the same as the other two graphs that I just saw before. Because we were able to implement the APPO algorithm, thanks to the asynchronous properties of this algorithm, we were able to have everything trained much faster. And for example, I think this took only 1.5 days to train. And we saw again, yeah, that the model managed to accommodate all the training data. What we want to see is not only memorization of the training data, but we want to be able to have models that properly generalize. But we're doing this with a bottom-up approach, right? Because we want to try to kind of avoid this. So this was we got this with a really complicated recurrent neural network model that had, I think, even a transformer in it that we took from paper because we said, okay, let's see if what they promised in the paper works. But what we're doing now is taking like a bottom-up approach. So we say, okay, let's train only on one day of data with a really simple multi-layer perceptron. Let's see if this works. So we saw that this worked, and then we say, okay, let's train on this one day of data with a more complex recurrent neural network. Let's see if this works. Okay. And what we're doing now is basically incrementing the amount of days that we feed it. So let's say, okay, instead of one day of data, let's combine the sampling and the 2 days of data. And that is the problem, that is the challenge that we have in our hands yet. We haven't gotten yet basically protocol to say, okay, when you want to deploy this in a real market setting, you have to train an X amount of days to deploy it on X amount of days. That is eventually what we want to accomplish. But we have to do a lot of experiments, and our hardware is limited. So we hope to eventually achieve this. I think I'm almost done here, right? Yes. As a kind of corollary, I want to mention some other things that I haven't mentioned yet with complexity of simulation. A really big one, and that all papers, of course, kind of ignore as well, is that we're simulating with historical data, right? So historical data is completely different from a real market, because in historical data, the data that you have doesn't change according to the actions of a given agent, right? And this is not the case in a real market, because in a real market, if you place a really big order, people, all the other market participants will react to it, right? So this is very unrealistic. So you saw, even without market impact, we have this problem of the dropping in the reward, but eventually it will be very desirable to have some kind of model that incorporates this market impact. But this is also very challenging because it has to combine all the historical data, and it has to learn market impact from historical data, and it has to work efficiently because it has to be incorporated into the reinforcement learning simulation. So yeah, this will be like the next frontier of our project. There is also the problem that I talked about under and overestimating the volume that comes from only having snapshots of the LOB. And then there's also the problem that in real markets, not only the first 20 levels of the LOB play a role, right? But there's also deeper levels of the LOB. It can be the case that there's volume at very unfavorable prices. And when we submit the market orders at the end of our simulation, this can also play a role, right? Because we only have recorded the 20 best levels of a given LOB, this is also not incorporated. But of course, this is a data limitation that yet again makes it so that we can really reach the complexity of a real market. In addition to this, there's also a lot of many more things in real market that we cannot incorporate into our simulation. So things like iceberg orders, things like I think they're called like snipping orders, something like this. Basically, hidden volume in black pools, I think they are called, where you cannot even see the order book of a given venue. So yeah, this is a simulation, and it misses a lot of very important features of LOBs in markets. But so far, you have to compromise for some things. So thank you very much. I will now pass over the stage to David, and he will run you over his use case.
And we move to our last talk, which will be given by David Jaggi. He is pursuing his PhD at the University of Zurich, and he specializes in artificial intelligence and machine learning with applications in finance.
Exactly. Thanks. So thank you very much. I hope some of you are still fresh for the last talk. We are now on the last stretch, so after me, you've done it. Yeah, welcome to this presentation about the reinforcement learning for factor investing. Thanks again for the opportunity to present here. A little disclaimer, we are currently, or we have only set up the environment at this time, which I will show you in a minute. And it would be very nice if you, I don't know, like there are some reinforcement learning practitioners who have way more experience than I have in reinforcement learning, and probably also some finance guys or girls which know way more about finance than I will probably ever know. So it would be nice if you could give us feedback after the presentation about what you would like to see changing within the environment. So, okay. So, quick outline. So first I will speak about the project, then a few points about me, just a brief introduction. Klaus already did it. Then a short intro to factor investing, since I assume most of you are more familiar with reinforcement learning, which Fernando already did an introduction. And then I will present the trading environment, which we have set up. Give you a little outlook, a small roadmap for the next steps we intend to do, and also allow for questions in case you have any in the end. So what's the aim of the project? The aim of the project is obviously to apply reinforcement learning to factor investing. What exactly is factor investing? I will talk about in a minute. So basically, the goal is to rotate between different factors which contribute to portfolio return in an optimal manner. As already outlined, the current state of the project is we are at the first stage. So we have now set up parts of the environment, or the first iteration of the environment. This is subject to change as we get more advanced, and we will have a bit more insights into what the interaction with the agent will be with the environment. And the challenge for us is, since this is a very practitioner-focused application, or we try to do the application very practitioner-focused, is that we present the environment as an asset manager would face it. So they have a multitude of constraints when it comes to trading. So for example, different weights, different turnover constraints, and so on. And that's different things we need to think about when we set up this environment. Yeah, we need to think about those in order to allow for a realistic simulation. So if you're a practitioner and you will take this algorithm at some point, you would see similar results in real life. So yeah, maybe about me again. So hi, my name is David. Yeah, I'm a researcher at ZHW at the Institute for Asset Management. I'm also currently pursuing a PhD at the University of Zurich, focusing on the applications of alternative data and machine learning in finance. Yeah, background is finance and engineering, and later moved to data science, and actually worked quite close to here. So, introduction to factor investing. What exactly is factor investing? So factor investing was pioneered by Eugene Fama and Kenneth French in the paper Cross-Section of Expected Stock Returns. You can also see parts of the abstract of this paper. And basically, they try to explain stock returns using different sources of factors. So you can think about it like the factors kind of drive the market. The paper was published in the Journal of Finance, which is quite popular in the finance space. And also, yeah, Eugene Fama later won the Nobel Prize. So definition, what exactly is a factor? So this sentence was taken from Investopedia, which is should be easily understandable. So factor investing utilizes multiple factors. So they currently, or in the paper of Fama and French, they used actually 3 different factors. Factors can include macroeconomic as well as fundamental and statistical ones. The factors are used to analyze and explain asset prices and build an investment strategy in the end. So the Fama and French model, very famous in the finance space. They developed this 3-factor model. The factors they included in their model were the size of the firm, the book to market, and also the excess return on the market. In the footnotes, you can see the link to Investopedia. I assume we can send the slides out at a later point. And also, if you are interested into the underlying data of those factors, Kenneth French has a very nice website where he uploads those factors data on a daily basis. What other popular factors do we have? I assume we didn't stick to those 3, which were developed in 1992. So we also have, for example, momentum, we have growth, we have market capitalization, and we have volatility. So those are just a very small sample of factors. There are hundreds of them. At the later stage, Kenneth French and Fama actually developed the 5-factor model, and also Posth and Stambo contributed another 5-factor model. So let's have a look at the factor performance. So this is a graphic which I took out of a JP Morgan Asset Management report. The date of this report was end of December 2021, so quite a few months ago. And you have to imagine during this time in December, on December 31st, the US actually had peak corona numbers. On the x-axis, you can see the different values. So we have or different factors. We have equity value, quality, momentum, and the size. And on the y-axis, you can see the absolute return. So as I mentioned, the numbers were recorded at the end of 2021. And the equity factors actually performed the strongest since the burst of the dot-com bubble. We can also see, if we dive a bit deeper into the data, that we have an asymmetrical factor performance. So the poor factor stocks actually underperformed the market, while strong factor stocks outperformed the market. Additionally, we can see when we take a look at the factors that certain factors react very strong to certain regimes within the market, and other factors perform poorly. So if we have a look at the behavior of those factors, we can also kind of imply in what regime we are currently within the market. So let's discuss our trading environment. So the environment we set up in the first step should be kind of like a trading interface an asset manager would be able to see. We have different components in this environment. So we have the data. We provide a configuration file. We have a rebalancing schedule. We also supply some indicators, and we also have some constraints which the asset managers face. Some of the topics should be familiar to you in case you have traded before. Yeah. For the data, we intend to use in the first step to factor ETFs in order to incorporate the performance of those factors over the time. Something which we have to keep in mind is that we take the fact of those ETFs from the same source. So the composition of those ETFs are actually similar to each other, so we can compare them. As the others already outlined, due to the limited amount of historical data, we might consider using a simulation or simulated data at a later stage. But simulating data will also come with its own challenges, and it will be a different beast to tackle, which we are not yet at that stage. So finally, some code, even though it's just a Python dictionary. So that's the configuration we provide to the environment. Yeah, if you have done some backtesting before, some of them should be familiar. So the environment or the asset manager or the agent has an initial balance. So that's the US dollar amount he or she can distribute among those factor ETFs. We also want to incorporate a benchmark. So the benchmark can be an equally weighted portfolio, for example, but it can also take any other shape or form. We can also incorporate, for example, stock indices to compare against. We have a start date and an end date. Yeah, that's between those we actually measure the performance. We have business day offset start date. So we, in this case, have 250 business days in which we don't trade, like the first 250 days. So we start after the first year in this case. If you have done back testing before, you should actually be very careful when you consider including costs. So keep in mind that every transaction is associated with a trading cost. Actually backtesting without costs and then running it live can break your neck. So be careful to incorporate costs if you try to outperform the market. We also have a reward scaling factor. That should be simple, and an observation price history. So that's how many steps into the past the agent can see the data. Rebalancing. So if you're an asset manager, or if you put on the asset manager hat, it doesn't make sense to rebalance every single day. Just imagine your banking advisor will call you every day and say, oh, today we shifted to stock 1. The next day he calls you again and says, oh, today I think we should shift completely to stock B. Doesn't make sense. So we actually provide a list of specific dates during the period on which the agent is allowed to do the rebalancing. This can be, for example, every first Monday of the month, or any other arbitrary series of dates. You can also rebalance on your birthday if you like to. Yeah, then indicators. So the current implementation allows for various types of indicators. Those can be of technical analysis kind. So for example, you are allowed to incorporate moving averages, relative strength index, and so on. Yeah, additionally, you can also include the portfolio composition. So for example, you will be able to, or the agent will be able to check back, like, how was the portfolio composition 5 periods before, and also, for example, the P&L. How did it develop over time? So we can do also something like portfolio sizing or trade. Yeah, so you basically trade less in case you experience a drawdown, or you trade more once you are your portfolio is in a good position. We also allow to include other time series like fundamental economic data, so GDP or unemployment rates. I assume this would be a bit more complicated once we move to simulated data. Then let's talk about the constraints. So one thing I already mentioned is, for example, a max turnover. So imagine on every rebalancing period, you're just allowed to move 5% of your portfolio. So you don't make too large of a rebalance. You can also think of having minimum and maximum weights per factor. So you're not allowed to exceed 80% of factor A in the portfolio and not allowed to have less than 20% of this factor. The constraints are currently very basic. So yeah, in case you are aware of any other maybe more complex constraints, yeah, feel free to tell them to us, and we will happily incorporate them into the trading environment. Little roadmap at the end. The next step will be to actually implement the agents. So we will be able to share some results. Once we have those results, we should actually analyze them. And then I assume we already exceeded the lifetime of the historical data. So we would need to tackle the simulated one just to be able to keep on developing the algorithm. Once we have the environment and the agent set up in this very simplistic environment with very few assumptions and yeah, very easy on the agent, we are then able to make it increasingly more complex. And I assume at this point, we're just then iterating, analyzing the results, tweaking some parameters, and see where we end up with the project. Actually, on the right-hand side, you can see the first plot. So here we just simulated, or we just randomly sampled some actions, applied them to the environment, and yeah, plotted the performance. So we have actually some nice charts. A bit of shameless advertising. So I think Klaus already mentioned it in the beginning. This use case is part of an InnoSwiss project, which we currently are doing without an implementation partner. So if you are a finance professional or also in another field, but have some finance-related research questions in your mind and you are open for collaboration, please feel free to reach out to us. We're happy to discuss those research questions with you and also work with you, and InnoSwiss might also be able to provide some fundings to those research questions in case they're applicable also to other financial institutions. So that's it. We reached the end. Do you have any open questions? Otherwise, I'm happy to discuss also after the talking post. Okay.